Good evening, everyone. Am I audible?
Yes, sir.
Okay.
Yes, you are audible.
Okay. So today we'll be doing the week three of the this live sessions for computational fluid dynamics. Let's start. So last session we were discussing on the variational formulations. If you remember, we were discussing like three ways we can represent a differential equation. So like let's have a quick recap of what we were doing. So we let's take the uh, basic uh, conduction equation. This. So this is the conduction equation. So uh, this is the conductance part, and here S is a kind of a uniform heat source that is applied all over the domain. And this equation, like we want to solve this particular equation. So for solving this equation only, we have tried representing this in a various other ways. So this particular form is also known as the strong form. So this form is known as the strong form. Why? Because this particular equation requires to be valid for each and every point across the whole domain. And whereas when we talk about the weak form, which is also known as this V form, there we actually do this kind of a formalism. So we take this whole left hand side of this equation and we take a variational parameter. Let's denote it by W, and we integrate it over the whole domain. Let's say we are heating of a rod, so 0 to L. We are anyway taking a 1D system, so we can write this. If it is a two-dimensional system, we can like integrate over the whole two-dimensional domain instead of what we are currently doing. So this is the weak form. This is the weak form. Not exactly this. If we we simplify this a little bit, what we will do is basically do some by parts operations, and then if we write it down, then we will get this kind of a this kind of a form. Plus, there will be some other boundary terms. So we discussed this in our last session. So uh, so this is also can be represented by a bilinear operator. This is the bilinear operator. Bilinear has some properties. What are the properties of a bilinear operator? Like this particular operator, bilinear is a property. So uh, bilinear is one of the properties of this operator. There are two other properties also, which are very essential for our uh, for a different arriving at different forms as well as for the solution. So, other than that, can anyone tell me what are the other two properties of this operator? So, anyone can unmute their mic and like speak, no problem. Okay. So, Bilinear, what does bilinear means? Bilinear means like it is linear in both slots that it has. There are two slots, basically two inputs that it takes. One is T and another one is W here. So it is linear in T as well as it is linear in W. If it satisfies both these two properties simultaneously, we also call it a bilinear operator. And other than that, it must be symmetric. It must be symmetric. What the symmetric means that ATW should be equal to AW. So A T comma W, this must be equal to A W comma T. And you can like see that these are valid for this particular operator. 0 to L K dt dx dw dx dx. So this operator, these properties are valid. Another one is positive definite. What is positive definite? Positive definite means basically A t comma t. If both have the same argument, then this is a positive term. So here also you can see like instead of w, if I represent by t, then this is basically dt dx whole square. It's integration. So any square term will be positive, and its integration over the whole domain will also be positive. So these are the three properties of this particular operator that we must keep in mind. And what about the this left hand side? This the right hand side. The right hand side will be can be represented by a linear operator. So this is a like linear and adheres to the rules of linearity, including the boundary terms. Where does the boundary terms come from? Boundary terms are basically the manifestations of the natural boundary. So the natural boundary conditions will we will find it here. What about the essential boundary conditions? For the essential boundary conditions, it like this will be like automatically come to zero because the W, this is the variational parameters at those points where essential boundary conditions are applied, the variation will be zero. So that was basically our point because like let's say if we have a term what which we will have here, if we simplify, we will have W K dt dx. This would have to evaluate at 0 and L. So let's say at 0, the dt dx is given, which is the natural boundary condition, and that is given to be 0. Then this term vanishes. If it is not 0, then what happens? Then we will have some w at 0 as extra this boundary term. It will be there. So dt dx is basically specifying dt dx in this case will be a natural boundary condition. And DTDS is therefore also known as the secondary variable in this case. What is the primary variable? Primary variable is T. Primary variable is T. Why? Because T's variation, which is W, is present here. So if T is specified, W will automatically be 0. So suppose like at L, T is specified, then this when we are evaluating this function at L, then this term vanishes. So the natural boundary conditions, non-zero natural boundary conditions will remain here, and that we have to keep in mind while we are solving different problems using the V form, which we will be doing. Another form which is there is the M form. What is M form? M form is basically representing this particular equations in a minimization statement. So this basically says that whatever this equation is, it is same as stating that we should minimize pi, where pi is equal to half a t comma t minus L. So this expression is there, and we have to minimize this. So it might be like a little bit feel a little bit different from what we are doing because G form and V form both are like basically equations. One is a differential equation, another is in integral form, but essentially both are equations. Whereas M form is a minimization problem; it is not a straightforward equation as such. But like physically, this is also very relevant because like this M form like in many a problems such as like finding equilibrium, what we aim for is minimizing potential energy. So those kind of problems are, you can see, these are like physically relevant problems which take this minimization form. And another, in the dynamics equations, we often like use the rule of limit minimizing the Lagrangian. So that gives us the Euler-Lagrange equation. So those problems are basically minimization problems, and this has similar roots basically. The minimization problem, like minimizing Lagrangian, if you convert it into a differential form, you will get the Euler-Lagrange equation. So these all are connected, and we can like transform from one form to the other. Okay. So like let's do a question based on this, and then we will move to the next topic. So yes, so like an equation is given, and you have to uh, select which are the natural boundary conditions and which are the essential boundary conditions. So let's solve this problem together. So the thing that is given, the equation that is given, what is this? This is in the D form, right? What is the order of this equation? Can someone tell me?
Sixth order.
Sixth order.
Sixth order equation. Okay. So now if we take it to the variation form, what might be the order of this, like of the variation in the V form? What will be the order? So what we will be doing is by parts operation, right? So this is there. This equation is there. We will simply integrate this, put a variation term here, and we will integrate this. So what we will do is repeatedly perform by parts till the like differential of this w and y, they are of the same order. So every time you do by parts, what happens? Like w becomes dw dx, and the differential here, this ddx operator, it loses 1 degree, right? So let's do that. Let's do this exercise. Hmm. So we have dq dx cube, right? This is our equation. So now what we will do, as promised, we will integrate this over the whole domain. So we will integrate this w. So we are trying to go from the D form to a V form in order to like say which is the natural boundary condition and which one is essential boundary condition. Actually, we will be able to identify this, like if you go through this exercise once, even without doing this calculation, you will be able to identify which one is a natural or an essential boundary condition. So, like for the sake of understanding, I'm like doing it once so that you will be able to identify. Okay, so let's uh, do by parts once. Hmm. So this is 0 to L. Yeah, the domain is from 0 to L. Let's do by parts once. So if we do by parts, the boundary term will be there. This boundary term will be W d2 dx2 ax d3y dx3. This evaluated at x is equal to 0 and x is equal to L, right? Minus, we will have this, the second term of the by parts. This will be dw dx. So note, w has gained the order of differentiation. whereas the other term has lost an order of differentiation. So this is there, and we obviously have this other term as well, which is the linear term, and it will stay as it is. Okay, all right. So now, can you tell me what will happen at x is equal to L? So I have this term W d2 d2 dx2 ax d3 dy dx3. This I have to evaluate at 0 and L. So the boundary conditions are given here. Hmm. So here all the boundary conditions are given. These are the boundary conditions. So let me write the term here and try to figure out what boundary conditions we will apply. Okay, so this we have to find out at x is equal to 0 and x is equal to L. So tell me what will happen at x is equal to L? Which condition out of this we will use? At x is equal to L, this is given, right? We have this term here, correct? So we will use this. And W will stay as it is. So this will essentially become W at x is equal to L into C3, correct? Minus, we have to evaluate at x is equal to 0. But you can see at x is equal to 0, y dy dx is given, d2y dx2 is given, but this particular term, that y we are here, this y that is here, basically that is not given. So what we will do here? We will use the fact that w is basically representing a variation in y. So if the variation is y is there at x is equal to 0, if y is specified, so here it is already specified 0. If it were not 0 also, whatever be the y specified, w we can take it as 0 because this represents basically variation in y. Okay, is that clear? Is the logic clear? So what is this? At x is equal to 0, these conditions are, so this will be 0. Right? At x is equal to 0, these conditions that are given, these are what? Natural or essential conditions? Can someone please say? The conditions that are given in this here in the at x is equal to 0, they are natural or essential conditions. So since it like we are specifying this variations at as 0, so these variations that are being specified, these will be essential boundary. Okay. And what about this y dy dx and d2y dx2? What are these called? These are called the primary variables. So these y dy dx and d2y dx2, these are primary variables. Okay. What about this x is equal to L? These will be called essential or natural? So these are basically natural boundary conditions. So these are essential, definitely. These will be natural boundary conditions. and these variables that are there, which are specified, these are called secondary variables. Okay. So, so yes, we were calculating this. So I'm not doing the rest of the calculation, but I guess you have understood. If there is any doubt, please don't hesitate to ask. You can like ask anytime, no problem. So what will be the next step? Next step will be to do a bypass of this. Then again we will have two terms. We will get a boundary term which will contain this dw dx and would contain ddx of this ax d3y dx3. So again, this is basically the secondary variable. If this is given, then this is a natural boundary condition. If instead dy dx is given, dy dx is our primary variable here. If that is given, then this particular term becomes zero. Dw dx becomes zero, and this is an essential boundary. Okay, so we will have to do two more iterations of differentiation till we achieve the V form. So what will be the V form? V form will be 0 to L, uh, in this case 0 to L d cube dx3. That's what I was asking basically, like what will be the order in the V form. So the V form, since we are having to do by parts three times in this case, we will get a third order derivative with W and third order derivative in Y. This is required because this particular term, we have already discussed, this particular term should be a bilinear operator, which is symmetric and positive. So to satisfy those conditions, basically, we need to have the same order of derivative both for W and Y. That's why we need to do this derivative three times to uh, come to the proper uh, V form. Okay, plus boundary terms. Boundary terms will be there because natural boundary conditions are there which are non-zero. So boundary terms. Okay. So so can you tell me which option is correct between these four? Someone please tell me. You can interact, no problem. There is
C
yeah.
option is correct.
Okay. Option C. Option C says that yes, these variables are natural boundary conditions. So that is true. So we just discussed.
Sir, why is
Yes.
d2y by dx square an essential boundary condition? Can you please tell me?
Yes, sure. So here basically we have discussed up to uh, like this step you understood. We are using by parts once. Hmm. So
Yes, sir.
after that the steps I have not done, but like if you do, so that's what I was yeah. So if you do by parts again,
It
you have
will
to do
go reducing the order for
yes,
the
correct. Hmm.
derivative.
So in the next step you will find a boundary term which will be this, correct, ddx of ax d cube y dx3. So this will be there. And you will have another integral which will be left over, where you will have d2w dx2. Is that understood?
Yes, sir. Yes, sir.
Yes. Now, if you do by parts of that term again, which you will need to do to arrive at this, then in the next step you will have the boundary term. This you will have the boundary term. Here you see that this is there. This particular term is there, right? If this term is there, uh, then what is the your primary variable for this boundary term? Your primary variable is d2y. Correct. Your secondary variable is this ax d3y dx3. Okay, is this understood now?
Yes, sir. Yes, sir.
Okay, so it depends upon your equation. In your conduction equation, you will see that dy dx itself is a secondary variable. Only the T temperature will be the primary variable because you will have only one boundary term. But in this case, this is a sixth order differential equation. So you will have three different boundary terms from each iteration of by parts that you are doing, and that's why like till d2y dx2 this is essential boundary condition, and like for higher order this will be till the fifth order term, it will be a natural boundary. Okay. Is there any other question? Okay, let's move to the, yeah, so this we have already discussed. So let's move to the next portion. So we will now do, and like, so far we have discussed different forms of differential equations, but that is not useful unless we know how to solve the differential equation using these like terms. So first we are going to discuss the weighted residual approach. So weighted residual approach, they are like this particular method basically tries to solve the equation as a whole. So let us see like what do I mean by that. So let's come to the conduction equation itself. Okay. So this is an equation. Let's say like we represent this equation using an operator like this. So basically, this is nothing but like signifying that this is an equation. So generally, L is written for like homogeneous linear equations, but like here this is not homogeneous per se because S is there. If S would have been zero, then it would have been homogeneous. But like in a more generic sense, we are representing this like L notation for these kind of equations as well. So let's say like this basically represents this. So LT equal to 0 basically means this equation. So what we are doing here, we will be choosing a approximate solution. So let's say T approximate is a like approximate solution that we have like designed for this particular equation. So we can evaluate this particular expression. Now this becomes an expression. So this will be some non-zero value, but this will not be exactly equal to 0. So what we will do is basically this minus, this is the exact one. This we will name as some residual R. So this is residual. Now to solve this particular equation, we will say to solve this particular equation, it means that this R needs to be minimized. preferably to 0. So like, and we will exactly like in the weighted residual approach, we basically do that. What we do is basically integrate this R, the residual, with a weight function attached to this. This is called a weighting function. We will like see what are can be the different types of weighting function now. So this integrated over the whole domain. So this equal to 0. This will give us the solution for the equation. So what we will do, like this is basically, it contains this T approximate. So if this T approximate has some kind of parameters attached to it, we can evaluate from this uh, like particular equation that we have like arrived. So, so this approximate solution, which is also known as trial function, this will give us the like this will give us the like nearby solution, the approximate solution that we will be hoping for. So how good is your approximate solution also like determines how good is the like um, uh, the solution that you are eventually going to get. You will not get the exact solution from this kind of methods. You will only get a very approximate solution. So here two things are there which we are needed to further like use this method. One is this tapprox, another one is this w. So tapprox is the trial function, and w is called the weighting function. And depending on like choice of weighting function, we will have different kinds of weighted residual approaches, and that's what we are like going to do right now. So if we come to the examples, this particular method will become more and more clear to you. So one of these weighted residual approaches, which is I think most intuitive to understand, is least square method. So least square method is basically nothing but we take the residual. So the residual we have already defined here. This is basically the residual. So we select a trial function, then we calculate the residual, and what we say is this integral. This is integration of r squared, the residual squared over the whole domain. This must be minimized. Why do we take square? Square is basically just to make this thing residual positive. So if we integrate just r, then we might be like um, there might be some positive residual, there might be some negative residual which cancels each other out. But overall, still we are having like non-zero values of residual there, and our solution will be very far from accurate. But if we take the squared, we now like all the negative and the positive values of r will give a positive value of r squared. And if we integrate this and try to minimize, we will actually get a very less amount of residual. And that will lead us to obtain a better solution. Hmm. So let's take an example. So let's say there is some equation like let's say d2y dx2 plus uh, x is equal to some kind of equation like this. So we have to first find like some like residual there, and we need to give boundary conditions as well. So let's say at x is equal to 0, y is 0, and x is equal to let's say at 1, y is 0. So we first have to design a trial function, the approximate like function. So this approximate function should at least do one thing, because we already have the like ideas of the endpoints. It must satisfy these boundary conditions. So not all boundary conditions are like required to be satisfied. Only the essential boundary conditions are required to be satisfied. That's, like you will see why like shortly. So these both of them are essential boundary conditions here in this case. So these essential boundary conditions must be satisfied by this y approximation. So what can be a possible function? So one possible function can be like design like this. So we'll like come to designing trial functions in a bit. So one particular function can be this into a. You can see if I put x is equal to 0, this is 0. If I put x is equal to 1, this is 0. So, and like a is a parameter that we have to find out using this least square method that will give us like the approximate solutions that we are searching for. This will not be accurate, but this will give us an approximation of the solution, and that's what we are looking for anyways. So this is uh, y approximate. What will be the residual? The residual is of y approximate minus the actual one. So the actual one is 0 anyways. Uh, what about this? This we can put here. So we need to find d2y dx2 for this. Can someone please like find this out? Only one term will remain here. What is that one term? The quadratic term, because we are like differentiating two times. So the first linear term will disappear uh, in the second derivative, and only the this quadratic term is there x that will remain. So what will be the residual? Residual will be minus 2a. You can check if it is correct. You like let me know if it is not. Okay. So this will be the residual that will remain. And now what we have to do? We have to minimize this r square. So integration of minus 2a squared. Oh, so sorry. This will be minus 2a plus x. X is there definitely. So this is, let me change this. Plus x. So this we have to minimize. Now what is minimization means? Minimization we can do simply partial derivative with respect to a and like equate it to c. So this is one like will like way of finding the minima basically. So and if we solve this, now you can see that x is under integration from 0 to 1. So this domain is 0 to 1. So this is under integration. So this x will we will get a value. So what we will have is basically an expression of a. So from here we can basically find out what a is. And if we find out what a is, we will get our approximate. Okay. Is the method clear to you? If there is any doubt, please like ask. And we will also like do some example problems after going through each method. So in this case, because like basically what we are doing is like differentiating with a parameter, this r square dx is equal to 0. This is what we are doing, right? So this can be, because a is not a function of x, so this can be taken inside, and what we will have is basically like r del r del a. So 2 will be there, 2 can be equated to 0. That is a constant. This will be equal to 0. So if you compare it with our weighted residual, what we like just now, the weighted residual expression. So here, the w that we have, the weighting function, this is del r. Del. So this is the least square method, and it's like the objective, the philosophy of this is very simple. We have want to minimize the residual. Okay. Similarly, another method is there, point collocation method, which also has a very simple philosophy. What its philosophy is there, like suppose we want some x1, x2, x3. Okay, by the way, if we have more parameters, if you want to have a more complicated function, we can also have that. Let's say you just don't want a quadratic, you want for getting a more accurate solution, you want a cubic equation. Then you will have two parameters, a1 and a2, and thus you will get two equations, one with a a1 in this case and another with a2, and you can find both the parameters from when you are doing partial differentiation with a1, you will get an equation of a1 and a2, and in the a2 also you will get another expression. From there, like two equations, two variables, you can solve it. And similarly, if you increase the number of parameters, you will get a more equations, and like computation will increase and your accuracy will also increase. So in this part, it is not necessary you need to take only one parameter. You can take multiple parameters as well. Similarly, in point collocation method, what we want is basically, like, let's say x1, x2, x3. These are some points, and we want like rest of the domain there might be errors, but here we want perfect solution. In this particular uh, points, we want the residual to be exactly zero, and that is what this is. So here, what we take is the weighting function that we take is uh, this is equal to delta function x minus x1. Let's say we are talking about point x1, then x minus x1 is our weighting function. What does that lead us? That leads us to this equation, delta x minus x1. This is over the whole. So this, like from the definition of the delta function, what this will be? This will be basically residual. So this is equal to zero. So this will be basically residual at x is equal to x1 is equal to 0. So whatever, again, like you can choose an approximate like trial function here. The trial function, whatever you choose, you will have to like evaluate this residual from there, like we had evaluated previously, and you have to set it at x1 equal to 0. So here in this case, if we had used uh, uh, point collocation instead of this square method, what would we have? We will basically have 2a plus x1 equal to 0. So we will have a is equal to x1 by 2. That's what we were searching for, right? A. So if you just put this like a's value here, we will get the approximate solution that we are looking for. Okay. So instead of just like one point, you can have multiple points as well. It will just like increase the number of equations. So one equation you will have with x1, another equation you will have with x2, like that. So you like increase the number of parameters in your trial function, increase the number of points. So like both must be same. If you have like one parameter, you must have 1 point. If you have four parameters, you must at least have 4 points. So you get the four equations so that you can solve. Otherwise, you will not be able to find the unique values for each parameter. Okay. All right. Yeah, let me know if there is any question. So another method that we will be studying is the Galerkin's method. So Galerkin method is basically like again, if we like take this particular example that we were using. So we were using this example. We were used to plus x equal to 0. This is the example that we were using. If we here the approximate solution, what we had used is a x 1. This is the approximate solution. So in Galerkin's method, the weighting function that we take is inspired from this trial function. So this is the trial function, and this is the weighting. So what we generally do is simply like make sure that the essential conditions are satisfied. Like a term that you might be seeing regularly is homogeneous essential boundary conditions are satisfied. So homogeneous part of essential boundary conditions are satisfied. So it basically means like if you have like uh, some function which is not giving zero at both ends, then like at least your weighting function, since it is like a variation that we previously discussed, like like primary variable, secondary variable, so the variation should be zero if it is specified. So it should maintain that. Okay. Uh, so so the weighting function here will be simply like x 1 minus x. We just remove the parameter. This parameter is not required, and the rest we take inspiration from the trial function, and that we use as the weighting function. That is the inspiration of the Galerkin's method. And the Galerkin's method, as you will see, like this is the basis of like the method that we that is very widely used in computational, like not only fluid dynamics but also like structural mechanics. Everywhere you will see this. That is the finite element method. So the finite element method draws its like inspiration from this Galerkin approach. Uh, yeah, so we will solve problems using these three methods. Okay. Uh, is this uh, if anyone has any questions, let's uh, do these questions uh, quickly. So we have the conduction equation and boundary conditions are given. So can someone tell me which one is an essential, which one is the natural boundary condition? Here.
First
Yes, sorry.
one is the essential.
Yes, the first condition is the essential condition. That is correct. So T is like specifying T is the essential. And what is this? This is the natural condition. Natural boundary. So so here we are asked to select like trial function. So what is the condition for trial function? Which might be a trial function or which cannot be a trial function? What do we have to check? We have to check for the boundary condition. Which one? The essential one. So this is the essential boundary condition, and we have to check whether this is satisfied by this trial functions given or not. So what about this? If I like substitute x is equal to 1, we get sec pi by 4. And sec pi by 4 is indeed root 2, right? Sec pi by 4 is root 2. So this is satisfying the essential boundary condition. We won't check for the natural boundary condition, that is not required. Again, like if we put 1 here, cos pi plus uh, sec pi by 4. What is cos pi? Cos pi is minus 1, right? So cos pi is minus 1 and sec pi by 4 is like root 2. So this gives us root 2 minus 1. So this cannot be a valid trial function. Why? Because it does not satisfy the essential boundary condition. So we have to check just for that. So this first one is correct. So it's like last two options are both or neither. So none of them are correct. So the first one is correct. Okay. All right. Go to the next question. Please ask if there is any doubt. Okay. All right. What does this question say? An equation is given and boundary conditions are given. I and also a trial function. So this trial function you can check for yourself if first of all that if, whether this trial function is actually like following this boundary condition or not. So if you put x is equal to 0, then this is 0. Sine 0 is 0. And if you put x is equal to 1, so sine pi, that is also 0. So this is the correct trial function. So we have to find the parameter a using least square. So what do we have to do? So Ly is given, y approx is given. So we have to find out the residual. The residual will be this d2 dx2 y approx plus 2 y approx plus this will be residual minus the actual term which is 0 anyway. So that we don't have to bother about this. So this is our expression. Please can you tell me what this expression stands for? Like what is the? Please do this calculation. So we have to differentiate this two times. So what is this d2y dx2? Has anyone found out?
minus a pi square sine pi x.
Yeah. So this will be minus a pi square. And you're differentiating a sine function two times. So this a minus sign will be there. Sine like it will jump from sine to cos, then again back to sine. And whatever the coefficient you have, it will be squared outside. So this is there plus 2a sine pi x. This is simply I have substituted this plus x. This is there. Now what is least square method? Least square method we know the domain is 0 to 1. So 0 to 1 integration 0 to 1 r will be there. And what else will be there? Del r del a. Right. This is my weighting function for least square method because we are minimizing r square. So this is my yeah. So dx. So let's just substitute all of this whatever we have 0 to 1 we have minus a pi square and pi x. We can group them together. So this is 2a minus a pi and pi x plus x. And if you like if you mm, partial differentiate with respect to a, then only like this x term will not be there. This will be there. We will consider x as constant because we are doing a partial differentiation. 2 minus pi square sine pi x. So you have some integration to do. Tell me how much this is. you have a calculator, you can like use a calculator to find these values. Mm. So these I think can be calculated in a calculator, right? If you have like using a calculator. If someone has a calculator lying nearby, please share the value. This is science. Okay. Like anyways, you will have this as your answer. To one. Okay. Whatever this comes out to be. So we evaluated this like a value of a to be substituted in our like approximate solution. Okay. So let us take a quick break and like then we can continue. Okay. Meanwhile, if anyone has done this calculation, you can report. Okay, let us. Hello, am I audible? Yeah. Let us resume. So you can work this out. This will be this can be evaluated in your like calculator as well. So whatever is, you can work this out. So here they are reporting B as the correct answer. You can check it and confirm it yourself. So we have the same question again, and now we have to use uh, the point collocation method. So collocation method, we are here it is given that x is equal to zero point 0.5. At x is equal to zero point 0.5, we want the residual to be exactly 0. 0. So, again the same technique will be there. We have already calculated the residual function. So residual we let us copy it from here. So this is the residual, right? This is the residual. So we'll like simply put it here. Okay. All right. This approach is actually point collocation is much simpler. Why? Like we have a delta function here simply. So r delta x minus zero point 0.5 over the 0 to 1. So what we have to do is basically at r we have to replace x as zero point 0.5. And we have to find out a. So can you please tell me what the value of a will be? This is you just have to replace x with zero point 0.5. Yeah, someone was asking reference book for weighted residual approach. So uh, basically, in any CFD book, CFD book or FEM book, a finite element method book, you will find weighted residual approach. You will also find like good study materials for weighted residual approach if you from Google itself. Like you might find notes from uh, other universities and from NPTEL also you may find some. Uh, if you want to read from a book particularly, then like I will suggest like a finite element method. Any book on finite element method will have a very comprehensive mention of weighted residual method. Has anyone evaluated the value of A? Please, you can talk. You can unmute yourself. No problem. Hello. Has anyone evaluated the value of A?
Option C.
Option C. Okay. So option C. So let's see once. So if we put zero point 0.5 here, we will have x is equal to 0.5. So sine pi by 2 will be 1. So we will have pi square minus 2a plus half equal to 0, right? So we will have, did I miss a minus sign somewhere? Oh, okay. Okay. So for option C is correct. Okay. Like before going to the next topic, like let's say if we want to calculate the same question using Galerkin's method, then what we would do? Let's say like we have the same equation and we want to use Galerkin's method. So what we would do? So there also we need to calculate the residual, which we have already done here. The residual is calculated, and then we would need to uh, find our function, and weighting function will be like inspired from our trial function. So here we will simply drop the parameter a and take the weighting function as sine pi. So sine pi x is there, this r is there. So simply we will do r into this w dx over the entire domain 0 to 1. This will be equal. So here everything is there, only a will be unknown. A is inside this r. So a will be unknown. So from here you have to find the value of a, and again this is basically it. So if you find the value of a, you will get the approximate solution that you were looking for. Okay. Let's discuss another method which is called Rayleigh-Ritz method, or also like this is the M-form method. So this is using the M-form. So what was M-form again? So M-form is basically half half is there, and we have half is minus Ly. This is there, and we have to minimize this. So if so related method is basically like we again take a y approximate. So this will again have some parameter. Let's say like again if we take the polynomial, then we may have something like this, and we will put it here. Instead of y, we will put this y approximation. And then what we will do? We have to minimize this. So what we will do is basically del pi del a equal to 0. So we partial differentiate with respect to a in order to minimize, and we equate that to 0. So then we will again get like an algebraic equation where we have to find out a. So basically all these methods what they are doing, you will find the common theme that we are trying to convert the differential equation into algebraic equations which are easier to solve. So if we have just the expression of like the value of a to find out, and like we will get this algebraic equations of sorts, and then we can like simply evaluate that algebraic equation to get a solution. And if you want more accurate solution, for example, like point co-location methods, etc. So point co-location method, we will simply add on points, we will add on parameters, we will still get a like nice algebraic equations, a group of algebraic equations, and if we solve all this, we will get an approximate solution. So that is basically the underlying theme with these kind of methods. So again we have the same equation. Now we have to use this Rayleigh-Ritz method that we just discussed. So for that we actually first have to find this A and L. This we have to do. Okay. So let's do that. So let's take this equation, uh, take this equation and find, try to find this A and L. Okay. So we will. So in the process of finding this, the V form to find this A and L, we will not utilize any we will not use this weighting function and all. So this will still remain V. Okay. Because we just need to find the this operator. We don't actually need to solve the equation now. 0 to 1. So now we can segregate the different terms. So y is there and this x is there. So this x will go in the linear term. So this yv, this will go in the bilinear term. So let us segregate. So we have this 0 to 1 v d2y dx2. I'm just writing the term separately, okay, so that we can evaluate this separately. So yv dx plus integration x d all of them from 0 to 1. So you can already identify actually this as in the LV form. This is there in the LV form. Hmm. And this one is already there in the AYV form, right? This one is already there. Only this is not there in any of the forms. So we have to break this. What we For that, what we can do? We can do by parts. So we will do by parts. So we have this v dy dx. This will be the boundary term 0 to 1 minus integration 0 to 1. We have dv dx dy dx. So this is again now in the form of a v comma y. So no problem. What about the boundary term? You can see like both of them are essential boundary conditions. So essential boundary conditions, that will get rid of this term. This will not be there. Boundary term will not be there. Okay. Now we can actually write this in the V form. So the V form will look like 0 to 1. This is one term of the V form. This is one term of the V form. So let us write 2yv, this term, minus dy dx dv. You can see this is also actually a bilinear operator. This is also bilinear operator. Like if means this is basically, you can also say it's a sum of two bilinear operators. So sum of two bilinear operators will always be a bilinear operator in itself. You can like yv term is there and this dy dx and dv dx term is there. Both are very like symmetric, positive, definite, bilinear. Every property it satisfies. So this term and minus 0 to 1 x. Okay. Now what we have to do? We have to use the M form. So let's go back to the previous page and like solve this equation there. We have space here. Write this expression here. This is what we are going to do anyways. So instead, I will write what is given. So I have been given this as my trial solution, approximate, uh, the approximate solution, and A I have found out. So I have to evaluate this expression. So let's evaluate this expression. Do the question with a different color. So A I know. So A is basically 2y square. So y approximate square. So this will be A square sine square phi x. And what it will be? Minus dy dx square. So minus dy dx square. So that will be A square. So dy dx. So what is dy dx here in this case? This will be A pi cos pi x, right? This will be A pi cos pi x. So this is A square pi square cos square pi. Please let me know if I am doing any mistake. Okay. So this completes my the bilinear operator. What about the linear operator? So I will now write down the linear operator. 0 to 1, 0 to 1. So this is minus x. So minus minus will become plus here, and x will be there, and this will be y across. So this is ax fine. Okay. Now what you have to do? You have to basically do an like partial differentiation with respect to a. So both these terms have a. Here a square is there. So this a square will be, like basically become 2a. So a I can take forward, right? This whole expression will be there. Only this a square term will be outside. You have to keep that in mind. Dx plus here this a term will not be there because like we are partially differentiating with respect to a. So x sine phi x dx, this will be equal to 0. Equal to 0, why? We are minimizing this. So here also you will get an expression of a. So you have to do some integrations. You can like use your calculator for that, or you can calculate. These equations can be calculated by hand. So do that as well, but it will take more time. Okay, so you can get an expression which you can find. So this is basically related. So this is giving us another way to calculate my approximate solution. Alright. So this you can like evaluate and please like check. So here the answer reported is B. You can cross check with that. Okay. I hope the method is clear to you. That is more important. The method is clear to you. Okay. If there is any question, please like ask me. All right. So next we will move to our next topic, which is the finite element method. So like so far, what we have been doing, we have studied like four methods. Okay, so one is the least square one, least square, uh, point collocation, Galerkin, and Rayleigh weights. Right, these are the methods that we have so far studied. So these first three are an examples of weighted residual approaches. And the like Rayleigh is like evolves from the M form. So these are different approaches. In all these approaches, what we have done is we have taken the whole domain. Like let's say like we were like solving some let's say we are solving conduction equation. So if we use these methods, so if we use this method, what we will do, we will take a T approximate solution. In these weighted residuals method, we will find out the residual, and then what we will do is like take the um, we will use the approximate solution to find out the residual, and there will be some parameters in this approximate solution which we will try to evaluate using different weighting functions. And what this will give us a approximate solution, but this is a solution for the whole domain. So if we are trying to like solve from 0 to 1, 0 to 1, we are guessing, first of all, this like approximation, we are like guessing a function, we are guessing for the whole domain, and this like and then we are trying to apply our methods. So whatever the approximate function that we will be getting, we will be getting for the whole domain. However, it is not like always very like likely we will be able to make accurate guess about the forms of these functions. So our accuracy will be limited in this case. So what does like finite element method and actually most numerical methods that you will commonly come across will do is it will divide the this domain into different parts. So it will divide the domain into different parts, and depending on the method that you are using, like this will be like named differently. For example, like it might be named grid points if you are using some finite difference method. If you are using finite element method, these points, these are called nodes. This will be called nodes. Let's say we put some node number 1, 2, 3, 4. So let's say we have 4 nodes. So these are called nodes. And what we have done basically is divided this whole domain into 3 parts using 4 nodes. So we have 3 parts. So these are called elements. So these are just terminology for finite element. These terminologies will vary from like method to method. So in this finite element, these are called elements, and the points are called nodes. And here in this particular case, the example that we have shown is a 1D problem. So here we have 2 nodes, 1 element. So each element will have 2 nodes I and J. Okay. So this is for a 1D problem. You might have 3 nodes as well, no problem. If like you have a node in the middle, like it means you might come across such examples like later on. So otherwise, like you can also think of like 2D elements. So if my problem would have been in 2 dimensions, I would have had a triangle as my element, where each element would actually have 3 nodes, or I can divide in like squares or rectangles as well, or quadrilaterals. So then I will have 4 nodes, or I can divide in more complex shapes as well, and my number of nodes will differ. And well, like so will be the calculations that are involved with it. In case of 3D, we can use like trigonal elements. So elements of these kind of shapes. So there are different kinds of elements possible. Number of nodes may vary accordingly. So let's first focus on like to understand what this the method itself. Let's first focus on this like one-dimensional element with two nodes I and j, and let us like use this um, this conduction equation as our example. So here, if we like try to means like do the same kind of like weighted methods, then what we will we would generally do, we would do an integration over the whole domain. Let's say 0 to 1, and we would equate this to 0. Uh, in this case, what we will say is we do not need to solve for the whole domain like means simultaneously. We can simply divide this into the elements. So this like integration is essentially summation. So we can like do summation over all elements, and each element we will integrate from I to j, and like this term will be there, this term will be there. So this is what we will do. And we can also argue that we do not really need to put the summation itself. This is summation is also for like we are doing it for the whole domain. This is also a weak formulation. So it should essentially, in strong formulation, this particular equation should be essentially valid for each and every point. So we can also write this for every element. This should be true. Yeah. So we can solve this equation for every element and then combine our solutions to get the solution of the whole domain. This is basically what is like the strategy. So first we are dividing this domain into subdomains, then we are solving for every domain, and then we are combining, we will be combining the solution to get the global solution. So this is what we are basically doing. So next we have to choose a trial function and all. So first let us like convert this into the V form. Then we can choose the trial functions to like arrange everything. Okay. So when we are converting this into the weak form, so this is equal to 0. So we will have the boundary term. So boundary term will be W K minus integration I to dx. Ah, mm, wait. So this is not required. There will be a W. Hmm. So this is our bilinear term plus our linear term will be there. Sorry, I to. So this is equal to 0. So this is all good. Uh, we can actually evaluate this right now only. So let's try to see what is our boundary term. So in this case, we do not really have any essential boundary conditions because we are solving for a generic element. So it can be the middle element, it can be the edges. So we don't know right now. So we will use the natural boundary condition. So we are not enforcing any essential conditions right now. So uh, if we use the natural conditions, so this k dt dx, this can be also written as the heat flux. So we'll use that. So generally heat flux, if you are like studied heat transfer, you will know like heat flux can be given like this. Out of an edge, if heat is flowing, so the flux can be given like this, and we will use this expression. So let's say at J, what will be this term? This will be W at J. So WJ, I'm writing this as WJ, and this k dt dx at J, which will be minus heat flux at J. Okay. Similarly, if it is evaluated in I will get this term. Okay. So I will use this expression. So let me write down what we have got so far. So we have got a bilinear term. We have got a linear term. And we have got this boundary condition. Okay. Now we will choose our trial solution. So let us say, like for this particular example, let us choose a linear trial function. So t approximate, I am writing t itself. So like since I am really not doing anything with the exact solution, so like I am not bothering myself to writing like approximately as a subscript. When I'm writing t, like it is now understood that I am talking about the approximate solution only. We are not anyway finding the original solution. So this I want this to be linear function. So something like ax plus b. Okay. So, but like a and b we can calculate. Then again we can like calculate this t. We will get the approximate for that particular domain, and again put that in the whole whole domain solution. We can get it from there. But this will be a little bit tedious. So a simpler way can actually be if I utilize my temperature at the two endpoints of the domain. Wait, yeah, yeah. So here, so so more interesting way to do this will be I have these points I and J. These are two nodes. So here the temperature, let us say it is Ti. Here the temperature is Tj. So these two are unknowns. So let us consider these as our parameters. So if we do that and try to write a linear expression, we can come up with this. So I think you can like find out a like means from here only you can, if we put this as boundary conditions, you will find the expression I'm going to write. But like I'm directly writing the expression itself. So this will be x minus x here by xi minus x here to ti plus xi minus x here, sorry, xi minus x xi minus x here into t. Let's just like try to focus what is going on there. So we can like confirm that this is the linear expression because we have only x here, no powers of x. This one, this. So we have x. So that give like that tells that this is the correct like means this is basically equivalent to what we were trying to find out. And this can be used as an approximate solution. Why? Because it satisfies the essential boundary conditions. So we have actually here imposed essential boundary conditions on itself. So means since we are like putting Ti and Tj as we are saying that Ti and Tj are the endpoint temperatures, we are exposing a like kind of an essential boundary condition. So my trial function should satisfy that. So that should be a requirement. So let us put x is equal to xi. If we put x is equal to xi, you can see that this becomes 1, this term becomes 1, this term becomes 0. So my temperature is Ti. And similarly, if you put x is equal to xj, you will see my temperature is T. So this is a like uh, valid trial function. The x is means uh, like linear. This is a linear expression. So we can also write this as ni pi plus ng. So this is basically a way to write this, like alternative way to write this. Here you can see this x is contained with this within this n. So these n expressions they have this x. So we have to keep this in mind. So these are basically functions of x. These are not like constants or any. They are functions of x, and these are also known as interpolation functions. They have a name. This name is interpolation function. Why this name? Because like basically if we using these functions we are interpolating the temperature value at any point inside the domain. So if we put x is equal to something and we will know what is the temperature t value. So what is like helping us to find that out is n. So these are called interpolation functions, and this we can in a very fancy way write like this. So this is a like a matrix notation, but you can see like if you do a matrix multiplication, you essentially get the previous term. This is a different way to write like this, and why we are writing like this will be very clear to you. Okay. Another thing that we need to do is find the weighting function because that also like we must substitute. W we need to substitute. And what we are using? We are using a Galerkin's method. So Galerkin's method will draw inspiration from my uh, trial function itself. So from this Galerkin's method, like the weighting function will draw inspiration. So this let me substitute it as okay. So this looks like this. What are these Wi, Wj? It can be arbitrary. It can be anything. So we are not bothered with that right now. So, but like this, like looks like this. This is the same function. This is the same linear function. So we can substitute this here. And this also like can be similarly written in this form. Hmm. Okay. Now, if we write this as this matrix N is Ninj and this as matrix T, then I can write this as W transpose in transpose. Why transpose? Just to like keep this N consistent. So N here is in this horizontal direction, N here was vertical direction, so I just like replaced. Okay. So time is running out today. So like I wanted to finish this out, but I guess like we will not have time to finish this introduction. So anyways, we would have done the problems related to finite element method in the next class. So like I will finish this up in the next live session, and we can then like do some problems with the finite element. If there is any question regarding like today's topics, or like anything that we have covered previously, you can like ask me now. So what is the like currently what is going on in the class? Which week's lectures are going on in your main lecture series?
Fourth week has been released, but assignments for third week are due tomorrow.
Assignments for week 3 are due tomorrow. Yeah, yes, I have seen even in the previous course, like generally these live sessions are like lagging behind. So you have this week 3 live session when your week 3 is going on right now. So that is still better. Like previous semester, I remember like it was 1 week behind. So week 4 was going on and week 3 live sessions were going on. So that becomes a little challenging. So anyways. Um, week 3 some portion is covered here, and I think like at least the uh, first part of the assignment should be like already covered. Some like finite element, some basic problems might be there. So finite element method we will like cover next week. Okay. Okay. So if there is no question, then like we can uh, meet again in the next week. So this will be uploaded to the YouTube. And yes, thanks for joining. Okay, I'll meet you guys in the next week.
Thank you, sir.